Okay, we will start. Welcome everybody to this webinar. My name is Gael Fretter. I'm the president of Polz and the lead developer of Polz and of Metalama. And today we have a webinar about a topic I love, and this is Roslyn source generators, a new feature, maybe 1 year old, of Roslyn and Visual Studio that allows you to generate code. But Stefan will tell us more about this. Stefan Polz, or flash over. Why flash over, Stefan?
Well, this has been my alter ego since quite some time. I used to be a firefighter. This is some years ago, and this is a firefighter term, and that stuck.
Okay. Stefan, you are a senior developer at Admiral Sportwetten in Vienna. You are interested and passionate by clean code, especially in C#, test-driven development. You like hacking with Roslyn, metaprogramming, source generators, and recently you spoke at NDC Oslo and many user groups. Before I give the floor to Stefan, the webinar will last about 1 hour. If you have questions, please use the Q&A facility in Zoom, and we will answer the questions at the end. I will repeat the questions, select the questions. Stefan, I think we can start.
Cool. So I take over the screen share?
Yes.
Well, okay. Hello world. Thank you very much for the introduction, Gail, and thank you very much for having me. I'm super excited to be here. I have obsessed myself with Roslyn in general and with source generators in specific in the last couple of years. So I'm really welcoming the chance to share almost everything that I know about them. So Gail already introduced me perfectly, so I will skip over that. Let's have a look what we are gonna inspect today. We have a look at what the source generators are at example. So with .NET 6, so source generators have been introduced with .NET 5. And now since .NET 6, the .NET team has actually built source generators themselves and shipped them with the latest .NET 6, with the latest .NET 6 SDK. And this will be expanded in .NET 7 already. There's something in preview already released. We will see what has been added to C#9, which facilitates source generators. Then we're gonna have a look at what is the power of source generators, but what are also their restrictions, how they look like, a lot about tooling, how we can get more familiar with Roslyn in general, source generators in specific, how to debug them, how to apply more recent C# features like nullable reference types to .NET Standard 2.0 libraries, some of the restrictions, we will hear all about that, different versions. Then we see a bit of a performance issue with source generators that we will then fix as well. Have a look at how we could publish our own source generators via Nuget as well. And at the end, there is some more examples and the Q&A section, and also a little bit of surprise from Gail. I'm very looking forward to that. So let's get started by example. In .NET 6, which has been released in November last year, the team actually built in 3 generators themselves. This one, which facilitates system text JSON, another one which is simplifying the use of logging, and actually also the laser, the razor C# file generated with source generators by now. So let's jump in right into code. The first example I would like to share is, zoom in. Okay, is logging. So here we have a simple usage about, we are creating a logger with the minimum log level of trace, and we will print hello world to the console. Let's see if this is actually working. And it does. Hello world is printed. Now we can also add, we can parameterize this logging. For example, let's add name here, and let's add this now to the parameter. So put world here. And this code now still produces the very same output. However, now there's a little bit of a caveat that we need to be aware of. Let me also show this by not passing a string here, which is a reference type, but actually passing an integer here, which is a value type. I will enter 0x_f0, which is basically 240. So let's see if we get hello 240 in the console. We do indeed, but there is something to be aware of here. We basically caused a little bit of a performance hit, because when I hover this log information to have a look at the definition of this extension method, we see that it takes a params of object array. Let's have a look at this in SharpLab. This will depict the problem. So let's do I have here this method. I do a params object array. Those are my args. Let's create a caller, public void caller. And this caller now calls into the method m with 1, 2, 3. But what is actually going on under the hood now? We see this on the right side. Here we create now, we actually instantiate this object array. The params, this is just under air quotes, just a C# feature. This has to be then, this is then compiled to something which can actually be 1. And we are more or less hidden, creating here an object array and setting these. Now, since this is an object array and we are assigning value types, the integers, those are structs, we also have boxing involved. So here we have some hidden allocations. Now to improve that, we, some time ago, with system text, with Microsoft extensions logging, there was also the concept of high performance logging. And this is achieved via the logger message.define method. So let's build a helper class. I call it log. And in here, now I want to do this. I now can define this message. So I have my static action. So this action where we first pass in the logger. Then we pass in the parameters that we have, for example, an integer, and there is always an optional exception as well, mark it as nullable. I call this hello. Now we must say logger message dot define, and we define this. So this is one parameter, the integer, and we can now define the log level. I do log level dot information, and let's say I want to pass in this 0x_f0 here, which is 240, and now the format of this message I just pasted in here. Now I want to call it. Maybe I want to call it via an extension method. So I make a public static void. I call it hello, and invoke this delegate that we've built here. So this is an extension method. So I say this ilogger, and we invoke that. With, of course, we also want to pass in the parameter. So this is my integer. I call this the number, and passing in as well. By the way, this is the event ID. So every log message also has an event ID. And we don't have an exception, so we can pass in null. Now we can invoke this extension method. So we can now say logger.hello and pass in our number. Let's use a different number. Let's use 9. So we now should have the same result. This time it should not print hello 9. Let's actually confirm that. Indeed, we have hello 9. So it's doing the same, but we now have, we got rid of both the object array allocation and the potential boxing for this params array. But this is now quite some code that we always have to write in order to have this performance improvement. So now comes one use case of a source generator. So there is 2 prime use cases. One of them is to reduce the implementation of repetitive code. Since this high level, this high performance logging pattern is always the same, I need to define my message and then actually invoke it. This could be done via a source generator. So the team has introduced a source generator for that. I will grab that example. I will replace that. So we now have our log message here. And that basically, let's change this to an integer. Set the 9. And we define that basically we control that via this logger message attribute. So I still do the very same thing. I have the 240 as an event ID. The log level is still information, and it's still the same format of a string. And let's see if we invoke that, if we indeed get the same result. And we do. We still get hello 9, but it's with much less code. And this is now actually generated by a source generator. But where is this code? Currently, I have a bug in my tooling here. Actually, get a compiler error, so in the IDE, but it actually, we saw it running, so it works. But where is this code? I can actually see that when we go into the solution we have, unless tooling doesn't show. I'm afraid tooling doesn't show this, but perhaps I can view the build output. Let me quickly grab that. It's not it. There we have it. So this is what's actually generated by a source generator. We see this is auto-generated, and it basically does the very same thing. It defines this action via the log message.define method, and also wraps this in an if logger enabled, which is always smart to do. Always wrap your log message in if it is enabled, because if we set up a higher minimum low level than the message is, then we don't want to print it in the first place, and we can avoid the invocation. And yeah, so this is one use case of source generators to eliminate repetitive code. Another use case is to increase performance. For example, we have system text JSON. So JSON serialization and deserialization. I will copy in 2 pieces of code, here and here. So what we're doing is, with .NET 6, new methods have been added to the JSON serialize and deserialize methods, which do take this JSON type info object. And this can also be generated by a source generator. So we define a partial method here, a partial class, which derives from JSON serializer context. We tell the generator for which entity, for which type it should be created, and can also pass in some options, such as that the output should be written indented. Here we define the entity that we want to serialize and deserialize. And then we do a little round trip. So we create the entity, we serialize it to JSON, print it to the console, and then we deserialize it again print it to the console. And let's see what's the output. And we do get, well, I do have a fail here because I put the log level 2 error. So we see that we first write this indented deserialized entity, and then again the serialized record. So this is the record 2 string that we see down here. And so the source generator now here generates a lot of code. We can perhaps see that. I'm afraid, not sure what's wrong with my tooling, but actually there is a bunch of code. I'm just opening one file because there is many. So this is like one file where the serializer options are defined, and this default deserialization context, which carries this type. So both this default serialization context and this entity type, they are both generated, and there's a lot of code. I will open another file and another file. So this is all generated, and the benefit now is that general or previous system text JSON without a source generator needs to do reflection. So it goes at runtime, needs to figure out, okay, what's the entity type? It has a string, which is called name. It has a number, which is called number, and has to figure this out at runtime. Well, they then cache the information, so it's only the first invocation, which is a little bit more expensive, but then this cache requires memory that lingers around in our applications. And source generators now do a very direct and already at compile time evaluated serialization and deserialization, which now avoids this startup cost. So we have improved performance, but also reduce memory allocations. And those are those two very powerful use cases about source generators. So we can get rid of tedious patterns to implement, but also potentially increase performance by most likely reducing system.reflection. So now we saw this partial keyword being used a lot, but this is actually C#9 syntax, because before C#9, if I do, actually let's show that in Visual Studio. If I would, let's get rid of that, create a public static partial class, let's call it helper. Now, and in there a partial method. I have it here. I call this method get. So before C#9, this wouldn't have compiled. Well, I do get a compiler error here, but I'm not sure what's wrong with the tooling, but this wouldn't have compiled because the explicit accessibility keyword was not allowed. Partial methods have always been, or so far have always been, implicitly private, because if there is no implementation to it, then the compiler basically strips it from the compilation. So this is also why it couldn't have return types. What wasn't also allowed, out parameters haven't been allowed in partial methods. Now with C#9, they are allowed, but if I now enter an explicit accessibility, such as internal, now the new rules, the C#9 rules, apply. And they state that it is okay to return something, out parameters are okay, but now the implementation must be provided. If the implementation isn't provided, they get a compiler error. Now the tooling actually fires this compiler error. Not sure what's wrong with my setup. seems that it can't find my source generator, but it's actually there because I wrote a source generator which looks for this partial method and actually provides an implementation for it. And let me show that. So if I do via the logger, or let's just do a console white line, and I say helper.get, and if I would run this, let me clear the console.net run, we actually get printed from generator. But we haven't written this. This is coming from a generator. Let's have a look at the generated file. Looks like this. So this generator now creates the second part. Let me put this side by side actually. So the generator creates the second part of this partial class and creates the implementation to this partial method. So this implementation with the new C#9 rule must be provided, but it may be provided by a source generator. Another C#9 improvement is module initializers. If I add a bit of code here to this helper class, we now have the module initializer attribute. And this is called whenever the module initializes. Basically, most of the times assembly and module, or at least in my mind, I'm not entirely sure what the difference between assembly and a module is. But basically when the assembly loads, then this one is initialized. And I can improve that if I call helper.thisText property. We have no code which actually invokes this init method here. We see this has 0 references, but still, I close the console. If we run this, we get this initialized string that's actually, that we actually set here. We never invoke this method, but this is done by with this new C#9 features module initializers. So our source generator could, or with module initializers, we could ensure that something is initialized that source generators require. And those two features now may be heavily consumed and used by source generators. Now, what are the laws of source generation? A source generator gets as an input the compilation of the user. So basically the user code, all the code that I have in my solution where I do include the source generator is basically put, well, not all of it, but most of it is put as an input to the source generator. For example, the C# code is passed to a syntax tree. This is very similar to other Roslyn extensions such as analyzers or code fixes. As a matter of fact, a source generator, technically speaking, is a Roslyn analyzer as well. So the programming model is very similar. So we get the syntax trees. We also get the semantic model that we can ask questions about. Is this identifier entity? What type is it? What members does it have? One limitation is we can only add new sources to the compilation. And those new sources are actually added as strings. So the input is the syntax tree, semantic model, additional files, and so on. And the output is basically a string. And this string now gets put back to the compilation and will be part of the final compilation, which will then be put into the DLL if we build it, or into the Nuget package when we pack it. And we can only add new sources. A source generator cannot modify or remove existing code. It can only add to it. So this is how this adds up with the partial, basically, extension point. A source generator can also produce diagnostics. We could, because technically speaking, a source generator is an analyzer, it could produce warnings. For example, if I misuse or if I misuse the source generator, then we could produce warnings to indicate to the user and guide them how to use them correctly. We can also access additional files. For example, we could mark a text file as an additional file, and the source generator, we could have something like a transpiler, which then spits out C# code from this additional file, whatever it is. Maybe we could transform JSON into some C# initialized dictionary, perhaps. Source generators are unordered. So if you have multiple source generators, they do not run, well, they do run in a particular order, but this is undocumented. So this may change. Source generators cannot depend on each other. So each source generator only sees the same input. They do not see each other's output. And I always said they're technically analyzers. And we went through the use cases, avoid boilerplate code, avoid reflection for better performance. In this presentation, everything you see is also available on GitHub. I put in documentations, also the cookbook, which is from the .NET team, delivers some recipes on how to solve issues with source generators. Now, what's the anatomy of a source generator? How does it look like if we want to build one? The most important thing is we need to include in our project, which has to be a .NET Standard 2.0 project, because source generators also need to run in Visual Studio. That's still based on .NET Framework. So for compatibility reason, just as any other Roslyn plugin, such as code refactoring or diagnostic suppressor, they have to be published as standard 2.0 packages. And this project then needs to reference the Microsoft Code Analysis C# workspaces. Maybe let me switch to red, should be better visible, yes. So this includes everything we need to build a source generator. This has been added in version 3.8.0, which is basically .NET 5. So this is only compatible now with .NET 5 and higher. So source generators don't work with .NET Core 3.1 or .NET Framework. We could still we could consume it in a project which targets .NET Framework, but this project needs to be built with the .NET 5 SDK. And additionally, I always like to add this set of analyzers. So this is basically an analyzer which analyzes the source generator that I built. So some sort of a meta analyzer, because it analyzes my analyzers. Always add them as private assets all, because we don't want these dependencies to transitively flow to the consumer. And then we create our generator. Our generator derives from source generator. This then defines, we need to define two methods. We have an initialize step, where we basically set up the source generator, and then the execute step, which eventually could produce, it doesn't have to, but could produce a C# string. And we need to put the generator attribute on top of the type so that the tooling, the driver, is aware of it. Additionally, we can define a syntax receiver. Actually, let me show this in action. So here, I will briefly show another example of a source generator. Examples, yes. If you have seen the talk from David Fowler, Implementation Details Matter, he showed the example of how enum.toString is a little bit slower than potentially anticipated, because in the background it does reflection, and it this reflection or this cached reflection values are then looked up in a binary via binary lookup in an array, and so this is not as fast as it can get. So one suggestion is to actually have a source generator which creates a more naive approach, which is basically just a switch over all the members of that enum, and then basically do a name of and print this out. And this is significantly faster than doing a regular enum.toString. So how can we create this code? So here everything is generated. This enum info type is generated, and all its members, and all its members are generated as well. So we see again the auto-generated on top. When we generate a file, always put the auto-generated on top, because this per default suppresses other analyzers to try to analyze our generated code, because the user has no direct control over how the analyzer creates these. And we see in the tooling that Visual Studio shows this file is auto-generated by that generator. We cannot edit it. Let's jump to that enum info generator. We see it needs to derive from my source generator, and it has the generator attribute on top. Now, in the initialize context, this is optional. We can register a syntax receiver via the register for syntax notification class, method. And a syntax receiver now is a type. It derives from syntax receiver, and it has one method. It has the onVisit syntax node. And this gets in each and every syntax node in the compilation. So basically the user's code. So just to give a bit of context, what's the syntax node? I will again jump to SharpLab. And exactly this code. How would this look like from a syntax tree point of view? I can switch to the syntax tree, and now we see the Roslyn representation of that code. We see this lives in a compilation unit. This is now our tree. We have a using directive, which is here. We have our class declaration, which is this entire type. Now this class declaration, it has a public keyword. It has two method declarations. When I jump in, then we will eventually find out that the first method declaration is this caller method, which has which return type is a predefined type, this void keyword. Actually, as a matter of fact, system.void exists. It's an unspeakable type, but it's basically there. And the second method is our other method, which has a parameter list. And in this parameter list, we have several parameters, where one parameter has the params keyword, and so on and so forth. And this we can keep going and expanding the tree. And each of these things that I can expand. So this is each a node. And those nodes now get supplied to this syntax receiver on visit syntax node. And now we can do filtering. So in the source generator, I basically, what we want to achieve, if I jump back to this example, what we want to achieve is to find every invocation of the enum info get name method. So we find all the get name methods which are invoked with one parameters. They are a good candidate for what we actually want to generate source code for. And this is basically what we do. So we check, is this syntax node indeed an invocation expression? So calling, for example, calling a method. We have a look at this invocation. If it has indeed one argument, then it's a good candidate. And additionally, we check if this expression, if it's a member access expression, could be something else. And we also check the name. So behind this method name actually hides the get name that we want to generate for. And all of those candidates, we can then expect further. We basically now get this argument expression. So we extract the enum constant that we invoke it with. So we basically extract this information and then put it into a list. And this list can now then be reused by the rest of the source generator. So with the syntax receiver, we can narrow down all the syntax nodes that we get to just a specific set of nodes that we may be interested in. And then comes the execute step. So in the execute step, we can now generate our source code. Let's have a look at this at the parameter, the generator execution context. So the generator execution context now holds all the information that we need. It has the compilation. It has pass options. For example, in the pass options, we can find out whether this project has been compiled with C#9 or C#10. There could be additional files if we mark them with additional files to the compilation. There is also config options. So we could provide settings, for example, via a editor config or a global analyzer file, or also via MS-Build. We could mark specific MS-Build properties and control the generation via that. We have our syntax receiver that we had a look on, and also cancellation token. So since the generator takes time, it's part of the compilation. If we want to abort it, then if we have a longer loop, we should from time to time try to cancel if cancellation has been requested. And now comes the meat of it. Here is our add source method, which takes a string, the hint name. This will be then shown in, for example, in Visual Studio. Per default, source generated files are actually not put to disk. They're just virtually there. There is an option to change that, for example, for debugging, but in general, they are not available. But we can supply a hint name for the tooling to show this, for example, up here. And then we have our string source, which is actually the C# text that we want to add to the compilation. So it is literally a string. It needs to be a string, a valid C# string. Otherwise, the compilation then would fail. So the generator could successfully generate invalid C#, which then would, in the second step after the generator is finished, fail the compilation. And with that, I now highlight the most interesting portions. Basically, first we know we have a syntax receiver. This is our enum info syntax receiver. I also check via the pass options. Is this C#? We can do this. This is like standard Roslyn. We can check if this language is indeed C#. I also get the options. So this analyzer could also via the analyzer options. But let's have a look at the generate source code. What I like to do is to use an indented text writer, so I can add tabs to the source code that I actually generate. But it could be any strings. There is different means. You could use a plain string builder or use other means of creating this C# string, maybe a more template-based approach. Everything works. What we need is a string. I always like to add the auto-generated on top. That's the first thing. What we also should keep in mind is the language version, because we could technically generate a C# string in our generator, but what if the consuming project has its language version set to C#9 or perhaps C# 7.3 because it's a .NET Standard 2.0 project, which is the default. Then, for example, with C# 7.3, nullable reference types are not available yet. So nullable enable wouldn't be meaningful. It actually would cause a compiler warning if this feature isn't there. So always check, or in this analyzer, I actually check, is this indeed at least C#8? And if it is, then we add the nullable enable. So keep in mind about what language version you want to support. Then we add a namespace, we add the class, and so on and so forth. And basically now compile our string that we then want to spit out to the compilation. And eventually We toString this, and at the very end, then add this to our compilation, and then we have it in here, and we can actually F9 it, F12 it. So actually, let's put this side by side and see the generator in action. Because if I start removing stuff from here, now on the right side, this actually gets updated. So if I remove everything, this here is the plain minimum that this generator generates. It basically just has a placeholder to enable IntelliSense. So I at least generate this enum info type with a get name, where we can feed in any enum, but we throw an exception. This should actually never happen, because if I start typing, if I say enum info dot get name, and now pass in an enum, let's use a string comparison dot, let's use ordinal. And now the generator picked that up. The syntax receiver found this candidate, and the generate and the execute step then added the source. And there we have it, a more performant way of how we could do basically toString our enums. Perhaps did I run that in advance? I do have a, oops. I must have deleted it by an accident, but I did run a benchmark. Perhaps I run it at the end, which actually shows now that this source-generated approach is indeed faster than the basic toString. Now, let's come to some tooling which could help us building source generators. Oops. I already showed SharpLab with the syntax tree. This is also available in Visual Studio. If I jump into Visual Studio, let's have a look at the syntax receiver file. I have here the syntax visualizer. I do get that if I open the installer, go to a modify, and select in the visual extensions I see this. Is this now enabled by default actually? I did now expect to see it's called the .NET compiler, the .NET compiler SDK. So this is somewhere that we need to select. It's not installed by default. I can't find it right away, but it's under this Visual Studio, and this Visual Studio extension workload. And when we install this, we get the syntax visualizer. And this shows now the same representation that SharpLab does, but basically in our code. So I can click here. If I click this field declaration, then it gets highlighted. So I see this is a field declaration, then I can jump into it. What are the nodes? How is this tree assembled? Another very handy tool is the Roslyn quota. This now goes in the other direction. So if you would like to find out the other way, so if I put in a string, let's say public static class my class. Now, what would I need to do Roslyn style in order to create this tree? So I can now generate this code, and I see down here, this is basically what I need to call via Roslyn in order to create a syntax tree which represents this string up here. So I create a compilation unit which has the class declaration, and this class has two modifiers, the public keyword and the static keyword, and so on. So this will go in the other direction. And there is also a source browser. Perhaps you are familiar with source.net. which is basically the source browser for the .NET runtime repository, where we can find types such as the cancellation token that I've mentioned previously. And we can then go to web access and directly jump to the source on GitHub. And this also exists for Roslyn. So there is source-roslyn.io. And if I would search the iSource generator interface, we see it. This is, and can also jump to the web access. Then we jump to the Roslyn repository and see how actually the compiler team is achieving all of this. Now I would like to show a bit about debugging. So in Visual Studio, we can mark a project via the is_Roslyn component, and also we can emit those compiler-generated files. This is basically what I showed. What I would expect is actually that maybe it works in this project. If we have a look at the, close that, at the example, we see this example now consumes the generator. In this case, I also need to set, because I don't reference it as a Nuget package, I reference the project directly. I need to tell MS-Build that this is not a library, but this is actually a Roslyn component. So I say, I don't want to reference the output assembly because there is no assembly I want to reference. I just want to enable this analyzer because source generators are technically analyzers. And in this case, I also set target framework. So this is how I can, for an example project, consume my generator directly. And if I go to the dependencies tab, let me open it and then show it? Yes. We see that here under dependencies, we have analyzers. This is the F0 generator that we have had a look at. Here is the enum info generator, and the enum info generator generates this enum info g.cs. So what you see here, this is this hint name that we give to the tooling so that we can display it here. And I can double click and then inspect what is actually generated. But also I can put this out physically to disk. So if I jump to this directory, we can go to the obj folder and have here the generated directory. In here, again, my generator, the enum info generator, and here is the same file. Or now here's the physical file, the physical representation. How this is enabled is via this flag, via both of the flags. We can emit those compiler generated files, and then we can tell MS-Build the tooling where to put them via the compiler generated file output path. I say the base intermediate audio output path, which is the obj folder, generated folder, and then we will find our generators in here. In order to enable debugging in Visual Studio, we can also set a debugger profile. We set this to the debug Roslyn component and can then actually debug into source generators. Let's see if this is working. So I will, if I have a look at so we see here, this is the generator project. Here is our .NET Standard 2.0 source generator. Here are the launch settings. And in the launch settings, I now say the target project. So the project which should be executed in order to run this generator. I tell it to use this example project. And let's actually select this now as a startup project, the generator, and do a breakpoint in our enum info generator. Perhaps that's just before we emit it. And there we are. And we see the hint name is this enum info.g.cs and the source text. Let's shift F9 that. So here we have it. This is actually our source text here is this string that we will output to the compilation. So this may help with debugging and stepping through code. There's also another way via unit testing. This is actually my preferred way. If we have unit tests, I can also debug. So actually, let's keep that breakpoint. If I go to my Enum info generator test, there it is. Oh, this is actually no, the wrong file. Enum info generator tests. This one. Yes. So if you're familiar with testing in Roslyn, the usual approach is to define an input string, and then we can expect an output string. So let's jump to, for example, this test. I do have here the string comparison, and I call this enum.info.getName. So this is basically the input text. And as an output text, I now expect what the source generator creates. So indeed, for this string comparison, this switch case that we want to generate. And we can then, with this tooling, assert that later on, we verify. And we can also just debug this test. To see then that we will jump in here as well. So debugging works from a unit test, in my opinion, better than via the debugging experience, because this also works for wider, for example. And it's always good to have a unit test. Speaking of unit testing, how can we achieve unit testing? So there is a package for that. There is in the Microsoft Code Analysis C# source generators testing.xunit. There's the XUnit flavor. This also exists for MS Test and NUnit. If we want to find out more about this, I also link this all in the presentation, but basically, if we search Microsoft.codeanalysis.testing, this leads us to here. So this is in the Roslyn SDK project on GitHub. And with that, we can test analyzers, code fixes, also code refactorings, and here our source generators. So with these packages, we can nicely unit test our source generators. And also what I showed already is from the consuming project, we need to set it like this. If it's packed in a Nuget package, the most important part is to keep in mind to have always private assets all. Speaking of Nuget package, I'm actually doing this right away. How does a generator look like in Nuget? So let's have a look at nuget.org. Let's jump to the generator that we showed, fco.generators, and inspect this in the Nuget package explorer. Now we see what's actually in this package. So we see we do not have a lib folder. We could have both. For example, the Microsoft.logging.abstractions. This both supplies a library plus the generator. Here, this is a generator only. So what we have is, since generators are technically analyzers, we see here analyzer in .NET CS. Here is the generator. And since this is not a library, we have no dependencies or no target framework dependencies. What we do have, since this is a generator, we need at least .NET 3.5 SDK in order for the source generator to work. Talking about nullable reference types. So one thing about source generators is, and this actually applies to all Roslyn projects, they need to be .NET Standard 2.0. But the default language of .NET Standard 2.0 is C# 7.3. But for nullable reference types, we do require at least C# 8. So what I like to do is always multi-target the analyzer to always target the latest .NET target framework so that we get the latest nullable annotations. We enable nullable. But now we need to be careful because an analyzer must be a net standard 2.0 project. So this is then for the Nuget package. I will show this also then in a second. We need to select the correct target framework. In order to get the nullable attributes, we can use this package, the Nullable package. And for the 2.0 target framework, we should actually suppress nullable warnings because the BCL is not annotated yet. So it wouldn't be very meaningful. Now, the Roslyn APIs, they actually are mostly annotated. Are they mostly? This is a lot of code, or at least a lot of it is already annotated. So these are fine. And we would now get, for the .NET 6 build, we would use that to get our nullable annotations right. But the net standard 2.0 that we do define as null oblivious, basically, yeah, we wouldn't mind because we already checked it for .NET 6 and we have warnings as errors, then we're fine, good to go. Now, I want to say a bit about versioning. So what I show so far is what has been added in Roslyn 3.8, which is basically the .NET 5 SDK. It requires at least Visual Studio 16.8 or wider 2020.3. Now in Roslyn 3.9, which is the .NET 5.200 SDK, which is available since Visual Studio 16.9, we have a new feature for source generators. Let me briefly show that. So here we now have a 3.9 generator. So this is basically how we control what feature set, what language set we have, what compatibility level, depending on the package that we consume. It's still a .NET Standard project. And what we have now is something called the post initialization. So we can register for post initialization and put out source code basically unconditionally. We don't have now this generator post initialization context. It is much slimmer than the other one. We have no compilation here, no parse options, no additional files. So we can basically do unconditional generation of code that we always want to generate. And now the thing is that other generators may depend on something which has been emitted by post-initialization context. Everything which is emitted in the execute step, we have multiple generators, cannot depend on each other. But everything which has been post-initialized may be there. I actually have here the evidence. So I have here a syntax node receiver. Actually, where is it? There it is. So in the execute, we have a look at the compilation. We get this post-initialization type that we do create here in the post-initialization namespace. We create a type called Roslyn 3.9. And we can actually assert that this is not null. So this really exists. And then basically say, okay, this type has really been found. So let's see what is actually, if this actually is there. If we again have a look at standard analyzers, here is our, oh no, in the example, of course. Here's our demo analyzer. And here is this post-initialization file. And this one we put out unconditionally. And the other one now says, okay, the post-initialization step is found, it is available. Now, while I have this open, I also want to show a bit of a potential performance issue because source generators may be invoked many, many times. So if I go to the demo, and I hope we can see this if I, yes, it works. So I just hit Control D to duplicate this line, and we see on the right side that more and more nodes are visited. So the more code we have, so this counter is actually, if we have a look at the generator, we do have a syntax receiver here, and the syntax receiver just increments the node visited counts every time it receives any node. And then we just put this out in this comment. We write it here. And this is what we see though, that the more code we have, the more often we invoke this method. And this is now invoked for basically every key press. So if I start typing a comment, now this is invoked. And if I add more code or add a new file, and the more I type, the more this is invoked. And if we have a small project, this is no problem. If we have a big project, it's most likely still not a problem. But if you have a huge project, for example, the .NET runtime repo, now this may cause huge performance issues. And actually, since this is within Visual Studio, is actually also called by Visual Studio, then may decrease the editing experience. And we may now experience lagging between our key presses because the generator or Roslyn in general kicks in all the time and emits every time, and with every key press emits everything anew. And this is not very fun to edit with. And this performance issue has been addressed with the latest version of source generators, which have been added now with Roslyn 4.0, which require at least the .NET 6 SDK, which in turn at least is available in wider 2021.3 or in Visual Studio 17, which is Visual Studio 2022. Which means now if we will upgrade our source generators from 3.8 to 4.0, now this no longer works with the .NET 5 SDK. We require at least the .NET 6 SDK. But since I think it's in May, .NET 5 is running out of support in May, I guess this is fine to do depending on your use case. Now, how does this .NET 6 style generators work? I can show you another project. This is yet another analyzer that we have a look at. For example, I will briefly show the example before. Let me change here something. Let's change this to, no, let's show this first. We have here a small program which uses a record class. However, a record class, so that this actually not the record feature itself, but the init keyword that a record is utilizing. If we have a look at SharpLab, I'll put in this record here, have a look at the C# version of the code, and let's move that. Yes, we see that in the generated code, this property that we had defined here uses the init keyword. This is compiler generated, but in order for this to work, we need there is external init type available, which is this one. I have 12 this, so this is available in the system runtime. But what if so this is available since, actually, let's have a look. Since when is this available? This is available since .NET 5. So I couldn't use this a record type in something lower than .NET 5. Let me change this to .NET 4.7.2. So I'm now switching to .NET Framework. Now .NET Framework doesn't have this type available. And although I set the language version to default, which is, I'm using the .NET 6 SDK here, which is C#10, and I build, this project still compiles because I have a source generator now supplying this type. If I have 12 this now, we will see this now is no longer the type from .NET, but this is now a source generator type. So the compiler basically just needs this type available in order for the init-only feature to work. And how does this generator work? This is now actually the newer version, a Roslyn 4.0 generator, which is called an incremental generator. And the programming model with incremental generators is a little bit different than with regular source generators. Under the hood, a incremental generator, as the name suggests, tries to do stuff incrementally. So we build up a pipeline, which then gets executed. And during this execution of the pipeline, the driver of the generator figures out which parts have already been executed, and if they produce the same output as before. because if the same output as before, or if they receive the same input as before, because if they receive the same input, we don't need to produce the output that we already cached before again. So with the combination of this pipeline and caching, Incremental Generator now can improve the editing experience for Visual Studio, so that we don't generate everything anew only because we hit a semicolon somewhere. Now, to mention that if we do a .NET build or on a CI system, there wouldn't be any difference between using, or no noticeable difference between using iSource generators or incremental generators. But from an editing experience, depending on the size of the project, the experience may vary tremendously. So with an incremental source generator, we only have one single method. We have initialize method. So the syntax receiver is gone, because the syntax receiver, this was, or could be, the potential performance issue, because it gets a lot of nodes all the time. So this is gone now. This looks now a little bit different. So we don't really have the compilation and the parse options and the additional texts. We don't have them available directly, but via this incremental value provider. And this is the core type that we use in order to build up our pipeline. So first, we have a syntax provider. We can create a syntax provider by feeding in two callbacks. We first have a predicate. This basically returns bool, which says, are we interested in the node? So this is now the comparable part to the equivalent to the syntax receiver. Let's have a look at this method, because this method now again gets in the syntax node, just as the on syntax node visited from the previous syntax receiver, and it returns bool saying, is this node interesting for us? Could it be a potential candidate for a generator? What we do in here, we see, is this a record declaration? And does this record declaration has at least one parameter? Because then init only property is emitted. The alternative would be if we have an accessor declaration syntax, basically if we define the init keyword ourselves. So here we have the explicit usage of init. Down here we have the implicit usage of init. And if it does, then this node is interesting for us. And then we actually do have to emit this type if it's not available. And the second method to this syntax provider is the syntax transform, which now basically receives the node, and we can return pretty much anything. We could transform it to whatever we need in order for our pipeline then to be meaningful. In that case, I basically just return the node, but we could turn it, for example, into a string or a collection of something. And then we combine that step with the next step of the pipeline, because now I need to find out if this type that I potentially need to generate is already there. So basically, do we have a target framework which already defines this type, or may this type is external init type already defined manually? And for that, we need the compilation, but we don't have the compilation directly. We only have, in the context, a compilation provider. Here, this incremental value provider. And this is now where the pipeline kicks in. So we combine that. We combine the compilation provider with our previous step. And then we get a combination. So this is actually this value tuple here, which now holds the collection of our syntax nodes and the compilation. I also want to see what language version this is. Is this actually a language version which supports the init only keyword? Because it doesn't make sense to emit this type. And for this, I need the parse options. So again, I now get the parse options provider and combine that with the previous step, with this tuple up here. And once I have combined, I could now also combine this with more. If I, for example, need in my generator, if I do need additional files, like the additional text, or if I do need the options, I can keep combining them until I have this one big provider that I then register my output with. And in this register output, we have here a tuple with multiple left and rights. And if I now jump into this callback, we actually see this tuple being fed in. And from here, we can now do our generation logic. So in our case, we find out, do we actually, is this external init keyword already defined in the compilation? What's the C# language version? And so on and so forth. And then eventually, again, from a generation point of view, it's very similar. It's basically the same. We need some string that we can then put out into our compilation. And then actually end up with this is external init type emitted if we need it. And this is now the different programming model of incremental generators. So this is a bit more, a little bit less straightforward, but eliminates potential performance issues. Basically mentioned that, yeah, so this is the consideration about performance. Whenever our source generator, they are not async, so they're all sync because, well, we are waiting for this compilation so that we can continue editing in Visual Studio and Rider. So if we're doing something more expensive or some longer loop, then regularly check if the cancellation has been requested already, because it doesn't make any sense to keep generating something which will be discarded anyway, or is already basically outdated. And we discussed the issue of the syntax receiver in huge projects, or a potential issue. Talking about Nuget. Now, if you want to pack this analyzer and ship it on Nuget, I briefly mentioned it already. What we want to do is to always set the development dependency to true, because this will then per default, if we .NET install this package, then per default we get the private assets all, which we always want, because analyzers per default shouldn't flow to transitive dependencies. And since we did multi-targeting, our analyzer targets both .NET 6 and .NET Standard 2.0, we need to select the correct target framework, which is Standard 2.0. Analyzer must be .NET Standard 2.0. So this is what we can do with this line. We indeed select the .NET Standard 2.0 target and pack it into this directory. This is where the analyzer lives in the Nuget package. We saw that already. And for the end, I would like to highlight, actually not almost the end, I want to highlight a couple of examples. So there is, I linked this all in the presentation. There is, for example, there is the C# source generator repository where the community has collected a lot of generators. So maybe there is one already in there which solves an issue of yours. Recently, also the community toolkit has been released, which has a source generator for, if I find it, component model, yes, for the iNotify property changed event. So iNotify property changed is usually something that is tedious implementation. It always follows a very similar pattern. So we can have a source generator generating this for us. So we have less, the user of this generator has less code to manage and to maintain. I also promised testing. I mentioned testing. So since with this testing package, we can very nicely we can debug analyzers, we can test our, generators. We can test our generators. We can also do code coverage on our generators, and also more advanced scenarios such as mutation testing. So I'm using striker.net here for mutation testing, and I want to show the report here. So let's have a look at the generator that we inspected, the Enum info generator. And we basically run the command line tool .NET Striker against it. And since we have basically our XUnit or NUnit or MS test suite, this works just perfectly. And we see, if you're not familiar with mutation testing, there is quite a lot of videos on this on the web. But if you are, we see we have killed a lot of mutants. A couple of them have survived. I seem to not exclude my debug asserts here. Let's see what else has survived. Here, these seem if we, let's see what mutation testing does. So mutation testing changes this greater than or equal to just a greater than, and then no test fails. So I definitely need to add a couple of tests to this very project. We can also do benchmarking, both our generators and also the generated code. With the generator itself, it's a little bit more tricky because the driver that we use does internally some caching, so we can't get, for example, with benchmark.net, not the most precise reports, but we could get an indicator where we basically, let's have a look at a example benchmark where we again feed in some source to this driver and then basically run our benchmark against where we invoke that. If I just briefly step over it, somewhere is a generator driver that we use in order to run the generator and update the compilation. And we can also benchmark the generated code. I'm afraid I might have deleted the report, but basically I here have a bit of a benchmark where I compare the generated version of this enum info.getName, but also the regular enum.toString and the already existing enum.getName. And here we would then see that the generated version, if I step into it, this is our generated version, is measurably faster and also allocates less than, actually allocates nothing. So this is also allocation free. And the enum.toString or the enum.getName actually allocates a little bit. And yeah, if you would like to know more about source generators in this presentation, I link here a couple of videos. For example, a recent video here is about how incremental source generators work under the hood and how this pipeline is internally managed, that the states are internally managed and updated or reused. And yeah, before we hand over to the Q&A section, Gail is about to show something very exciting. I just want to have one more note. So if you have later on after the Q&A some questions, then you may contact me on Twitter. I am also now Twitch streaming on Flashover, twitch.flashover. And actually in 2 weeks on Saturday, I will be doing a live stream on source generators where we will build live a source generator. All of the source is available here. I will put it into the webinar chat if you want to check it out later.
Thank you, Stefan. It was amazing, very detailed. I learned a lot, even if I worked, I've been working with source generators for a couple of months and didn't know everything. I would like to show a product that actually we've just released a preview of this week. Let me share my screen. I will do a very short introduction to this. I need to. This is this. No, it's not the right. What I'm sharing here. I'm lost. I'm sorry, I'm lost with the sharing. I'm really sharing the contact list or not? No, okay. Good. So I'm back. So what you have shown, Stefan, this is actually, from my point of view, very low level development, because you need to cope with the syntax nodes, with the semantic model, and I think that what what Microsoft did with that is a kind of low-level API to extend Roslyn. And there are many of these APIs. You mentioned analyzers. There are also suppressors. There are code fixes and code refactorings. And we have built a product evolved from PostSharp, the same kind of product as PostSharp, for high-level metaprogramming. So you can do all these things, but without going to the syntax node. And the concept of MetaLlama is that we have a templating language that we call T#, like templating for C#. And this is an example of a template that does logging. So this is the template. You see what is great here is compile time. So this is a compile time expression. So we are entering a method. Meta.proceed here is the call to the method that we are templating. And then after that, we are writing another message. So I can apply the template to any method, and I can preview what the template does to my code. So you see here, we are doing code generation, but there are big differences with the Roslyn code generators because we are able to modify a method itself, not just a partial class. So it is not additive only, it can also add things. So this is one example. Another simple example of a template you may do is, for instance, retry. Here we may, like we are invoking the method inside the loop. Inside the loop, we have also a catch, and when we can still retry, we are just sleeping and looping. So if we apply this retry to a method, and I show, and I'm doing the preview, we can see what MetaLlama will do with the code. So the difference is that here it would do this with the code at compile time, because at runtime it doesn't want to edit your code. There would be no point. And you can also do more complex templates. So here I would like to do logging with parameters. So instead of just saying I'm starting the method, I would like to have the method name with the parameters. And I could add another parameter and see what it is doing. So I can do the div, and this aspect or this template, we can call that an aspect, is printing the name of each parameter. So it's actually just a more complete, more complex template where we are creating an interpolated string builder. We are going through the parameters. We are adding text tokens. And you see, this is C#. It is not Roslyn programming. It is C#, like it's the same level of abstraction of programming as you are using when you are doing UIs, WES, business applications. You don't need to go into the details of Roslyn. And we can also do what source generators can do, like introducing new things. Like here, this template that we can apply to a type, we are introducing a property into that type, and I can do the preview to see what's happening. So the good thing is that we can combine. So you have shown the implementation of notify property change through source generators. I frankly believe this is a shame, not of you, Stefan, but of Microsoft to show notify property change as an example of source generators, because what they do is that they are transforming fields into properties, generating fields from properties. So actually, you are losing the like idiomatic C#. It's no longer C#. What you are doing is just hacking. So the So we know how to do notify property change. We've done that for 10 years. You don't want to change your fields into, no, your properties into fields just to have your source generators to work. So here we have a more complex aspect that actually combines two things. We are introducing a method, we are introducing a property, we are implementing the interface, and at the same time, we are changing all property setters to detect a change in the value. This is the right way to do that because your existing code doesn't need to be changed. Like source generators can be abused. They have been abused. You should not do that. That's a matter of opinion that we could discuss. So now, if you apply notify property change to an existing code, actually what it's going to do is to change your code to inject the logic. It applies the templates. And you can notice that we can actually call from the source code, the code that has been implemented, something that was not possible with PostSharp because we did that at post-compile time. And this is because we are able to do that because we integrate with source generators. So here you can see that we have our source generators, which defines the new methods. You will see these new methods are not implemented. I believe there is no point at all in generating at design time the bodies of methods. It just takes CPU time. It is useless. It's only useful when you compile that. So so we don't do that. We only define the declarations, not the body. Now, if you choose here llama debug configuration, you can also debug the source that that we have produced. So you can debug the generated code, the transform code. Now you get into the property setter. So we have that, and that's all I wanted to show today because there is a lot more. You can also emit warnings, suppress warnings. I've shown that you can do code fixes and code refactorings using templates. I didn't show that, and I also show. I have also shown the code transformers. That's all I wanted to show today because that's not a webinar about MetaLlama. But if you are interested, there are two things you can do. So if you're interested to try it today, you can go to the to our website, postsharp.net, and to the MetaLlama section. There is also a sandbox, an online sandbox, actually a fork of try.net, try.net. So this is a fork where you can try MetaLlama without leaving your browser. The next webinar on March 15th will be about MetaLlama. The exact time is not decided yet, but we will perhaps do two times in the day, one in the European afternoon, the second in the European evening. That's all I have for MetaLlama, and let's see if there are questions. To see questions, I may need to stop sharing. And I don't see questions. But if there is no question, I have one question actually. You have shown mutation test. Could you elaborate? It's the first time I heard about mutation test, and I would like to hear what is it I'm missing.
Perhaps let me briefly dig out the example that I have. There's actually there was actually a mutation testing talk that I also gave at the NTC Oslo. So let me fire up that solution. I like to show it by example.
You need to share a screen again.
Yes. Yeah. I'm on it. Oops, don't want to cause any recursion. So, and so in this example, let's actually run all the tests and see if everything indeed turns green. And I have a build error. Oops. Let me briefly get rid of that by terminating global JSON. I believe I'm pinning to an older SDK version that I no longer have. And the example, for example, is I have here a naive little calculator where I can add numbers, I subtract numbers, I can multiply, and so on and so forth. And actually, I do have a little bug in here. I do have in the divide method, I have here by accident also a multiplication. So I know I did a bug here, but what troubles me now that all my tests are green. And actually, if I would do a code coverage report on that, I would see that I have 100% code coverage. I got everything covered. Let's actually jump to the tests that we have here. So I call this divide. I divide 1 by 1 and expect 1. And I divide 240 by 0 and then expect this NIN that I defined. I could also throw an exception. So I have 100% code coverage, but I did not discover the bug here because my test suite isn't good enough. And this is what mutation testing now uncovers. So what mutation testing does, it has a look at the tests, sees what is the project under test, and then from this project under test actually mutates the source code. So it goes ahead and changes, for example, this addition to an negation. So it created one mutant. Now, with this modified source, now all the tests are run again. Or at least all impacted tests, which is tests which actually now cover this production line. And now we expect at least one test to fail. And it does. So we see here, at least one test is failing, and this is good. So we have produced a mutant, but now one test is failing, that's good. So the mutant has been killed. So we not only cover, where is it? So we not only cover this line of code, we also have an assertion that protects this line of code, or this very statement. And then mutation testing continues and changes it. Again, for example, minus to a plus and so on and so forth. And eventually down here now would change this multiplication, for example, to a plus, something else. And now I got, actually changes in that case to a division. Oops, I hit debug. And we see now we have no failing test. Although we changed this, basically we fixed it, but we have no failing test, which means that this line isn't, well, it is covered, but it's not 100% asserted. So changing the code won't make a fail test, and now a test to fail. So I could now add a better test. Let's say I divide 4 by 2 and expect 2. And with I restore the original code. And now I have improved my test suite. And now my test suite fails. And now I really discovered that bug. So mutation testing, in short, it creates mutants of the production code. And each mutant expects at least one test to fail. And if a test is failing, the mutant is killed. That's excellent. And if no test fails, then the mutant survives. And we then, at the end, at the mutation coverage report, do I still have it open from previously? No, I'm afraid I don't. But in this mutation test report, we then can see, okay, what has been mutated? Where is our test suite not 100% effective yet? So we can improve our tests and eventually then fix more bugs.
Okay. We have a question from the audience. Do you know if .NET if the .NET Standard 2 restrictions for source generators will be changed in the future, so we can use later target frameworks like .NET Standard 2.1 or higher.
I'm afraid I don't know that. I'm not sure. I believe, but this is my understanding of it, that as long as Visual Studio is working as it is and is on .NET Framework, then the .NET Standard restriction will keep alive because, for backwards compatibility. If there are any plans to change this in the future, maybe there is a different solution around it, but I'm not aware of that, I'm afraid.
Yes, I agree.
This not only impacts source generators, this impacts Roslyn plugins, like code fixes, analyzers in general.
Yeah, we had the same discussion internally, and it needs to stay .NET Standard 2.0. The way we solve that in MetaLlama is that only the compile time code needs to be to .NET Standard 2.0, because actually when we compile your project, we split it between runtime and compile time. But anything that is compile time, it's actually it must be .NET Standard 2. Mm-hmm. I was disappointed to see that Visual Studio 2022 was on the .NET Framework runtime and not on the .NET 6 runtime. That would have solved a lot of problems, but I think it is not so easy. We have another question. If we don't emit the generator to disk, which is recommended, I believe, does this affect the debugging experience? Like, if I want to step into the generator code from this project?
I hope I understand correctly. Actually, it's the other way around. So so for production projects, it's not recommended to really emit the files to disk. Those are just under air quotes for debugging, because it will take additional resources to put this file to disk. So we need to enable that per default. They are not emitted to disk, so we need to explicitly enable this for this debugging experience that we can view. For example, what I like to do is then have in a second screen the generated file in while I edit the source generator. So per default it's off. For debugging we need to enable it, but I don't recommend to enable it for the production project itself. I like to enable it for a small testing project. I always have a sample project where then actually integration test the generator.
Yeah, I think by default the files are in the PDB, so the generated files are in the PDB. I'm not sure if it's in all PDBs or just in the new PDB format. Do you know anything about that?
Oh, I'm afraid I don't know.
So pay attention. Actually, you should not ship your PDB if your source code is confidential. But with source generators, your PDB really contains source code, but only the generated one.
Which is also now an interesting thing to be careful about. This applies for every Nuget package, but from which source we consume source generators. Well, we could depend on a malicious package, which has malicious code, which may maybe read my local files and puts them to a server. But we could also, with a source generator now, an attacker could have basically access to our source code, to a source tree. So if we consume, so from a security point of view, this is something to consider safe sources for our generators, because they could be technically abused for an attack or for malicious evilness.
You mean because the generator or the analyzer runs inside the Visual Studio IDE?
Not in general in Visual Studio, but so not in specific in Visual Studio, but in general.
Yes.
Since the Visual Studio the generator sees the source. Now the tooling could put it out to file for us to debug, but an attacker, a malicious package, could put this to some server and would leak our source code. Yeah.
But it was there from the beginning of Nuget. You could have an MS build task that was a DLL, and then you got access to the local machine.
Oh, okay.
Yeah,
I wasn't aware of it.
But now, like in the beginning of Nuget, it was a problem. So actually, companies they didn't allow. Well, not all companies, of course, but like corporates didn't allow to consume packages from Nuget.org, but they had their own repositories of curated repositories. But now there are decent security settings on Nuget, and you can define trusted publishers. So for instance, we are signing all our packages. So if you trust us, you can add our signature to your list of trusted publishers. But yes, the risk was always there. If you consume a Nuget package, you just open the doors of your computer to the author. Good. We have run way over time, but it was very interesting. And I guess people who were not interested left already, so we could continue. But anyway, I don't see more questions from the audience. So Stefan, thank you very much for this evening, for this presentation. It was very interesting. And next month, there will be more detailed presentation about MetaLlama based on source generators and analyzers and all these technologies, no longer on MSIL. And if you want more details faster, you can go to our website today. Thank you very much. I'm going to stop the recording and stop the webinar in a minute. Thank you and bye-bye.
Thank you very much. Thank you for having me. I had a lot of fun. And I'm looking forward to the MetaLlama presentation.
Thank you. Bye-bye.
Goodbye.